Today we're going to talk about section 5.1 from our book, which is how to find extrema on an interval. So let's review a little bit about extrema. Now, an absolute maximum means the absolute biggest value of f of x. So if you're thinking about a graph, it's the highest point that graph ever reaches. And the absolute minimum is the opposite. It's the smallest or the lowest point that graph ever reaches. Now those two things together, the absolute maximum and absolute minimum together, we call extreme values or extrema. So basically, don't get these mixed up with our local minimums that we've been finding, local minimums and maximums that we found with the first derivative test. This is a little bit different. We are looking for the absolute minimum and maximum. So let's talk a little bit on interval notation before I give you our next theorem. We've been using interval notation actually kind of a lot so far. We did the first derivative test and concavity, and for both questions I would ask you, okay, now tell me the open intervals where this function is increasing or where it's concave down. And your answers look something like this. So I said, for example, if you have in parentheses -2, infinity, what it means is all the numbers from -2 to infinity, but not including -2. That's what makes it an open interval. An open interval doesn't contain its endpoints. Now starting today, we're going to be talking about closed intervals. And a closed interval is exactly the same thing, but you use brackets or the square parentheses instead. And that means it's a closed interval and it includes the endpoints. So for example, I might say something like this. Now it looks very much like this one up here. The only difference between the one I circled and the one I wrote below is that the one I wrote below actually includes the number -2. -2 is part of the interval because I put a square bracket on it. Now the one up top, I didn't, so it doesn't include. It means every number bigger than -2, but not including. The bottom one does include it. Now notice I put a parentheses on the infinity. You can have one of each like that. You can have both parentheses, both square, one of each on either side, because either number that it's attached to, that's what you put the parenthesis or the square on. Now, with an infinity, you never put a square bracket on that. You never put a bracket because that means to include the number, and remember, infinity isn't really even a number. So you should never have a square there. But you can have one with square on both sides. So I could have an interval that goes from -2 to 5. And that includes both the -2 and the 5. Or I could do something like this. I could say, well, let's do this and not include the -2, but do include the +5. So you can have any combination of, you don't have to have both parentheses or both brackets. You can have one of each. And just remember, other than infinity, which always gets a parenthesis, the number itself, whichever it's connected to, tells you what to do with it. So because the 2 is connected to a parenthesis, you don't, the -2, you don't include that number in the interval. But over here on the right, the 5 is connected to a bracket, so you do include that number. So that's a review for you guys on how interval notation works with open and closed brackets. And the reason I wanted to review it is because there's one included in the extreme value theorem, and that's our next thing. So we're going to learn the extreme value theorem now. And what it is, you can tell from the name, it's a theorem about the extreme values, about the absolute minimum and maximum. So what it says is, if f is continuous on some closed interval a comma b, so it could be continuous from 2 to 10 or from -5 to 7 or something like that, but closed interval, brackets on both sides, then it definitely does have both an absolute minimum and maximum on that closed interval. And I'm going to show you a quick picture of what that looks like. So let's say we have a function that looks like this. And when you look at that picture, remember the first time we talked about this, I said this does not have an absolute minimum or an absolute maximum. When you have that arrow that just kind of continues on forever pointing down, it doesn't have an absolute minimum. It keeps going smaller and smaller and smaller forever. And same thing with this arrow over here. If you have an arrow pointing up forever, then it doesn't have a maximum, an absolute maximum. So the graph I've shown you so far has no absolute minimum or maximum. But let's do this part. Let's put it on a closed interval. So let's say that, I'll just kind of put some here. Let's say this is A here, and this is B right here. By putting it on a closed interval, what we're saying is the function starts right here and ends right here. See if we get a better color for this. Starts right, we'll go back to yellow. Starts right here and ends right here. We're basically chopping off or getting rid of the ends of it. Now by chopping out a middle segment of your graph, cutting off both sides, the left and the right, then basically the piece that's left over, you got rid of the arrows that were causing it not to have a minimum or a maximum. So it definitely will have one of each. This graph right here looks like it probably has a maximum right here because of that little part that's left in the middle that goes like this. That's the highest part, and it probably has a minimum somewhere around here. So that's what the extreme value theorem says. It says, yeah, it's okay for a function to not have an absolute minimum or a maximum. But if you chop out a segment of it and just look at that part, then it definitely will. Now, also, let's talk about one more thing here. It says it has to be continuous. So what that means is, let's say you have a function with a vertical asymptote. Say you have a function like this, and the function goes up here and maybe down like this, and I say, okay, now let's do that same thing we just did. Let's put A right here and B right here. All of a sudden it doesn't have a minimum or a maximum still, because in that interval between A and B you have the arrow going up and the arrow pointing down. So it does have to be continuous for this to work. But as long as it is, as long as your graph is one single piece all the way through and you chop a segment out of the middle, it will definitely have both an absolute minimum and an absolute maximum. And both of those things, the absolute minimum and maximum, will either happen at a critical value, like when we did first derivative test, or one of the endpoints where it starts or stops. So this is how we're going to do our extreme value theorem. Questions. I'm going to ask you a question like this. I'm going to give you a function and I'm going to say, I want you to find either the absolute minimum, the absolute maximum, or both on a closed interval. So step one is kind of like first derivative test. Find the critical numbers, meaning take the derivative, find out any places where it's either 0 or undefined. Now notice here I said even in italics, I wanted it to stand out. I said you want to find all the critical numbers in the interval. We're only focused on that interval. So like if my interval is going from 0 to 10 and I get a critical number of 20, just throw that one out. It's not in the interval. We don't care about it. If I get a critical number of 5, something that is between 0 and 10, I keep that. Now, don't do the first derivative test. You found your critical numbers. We're not going to make a number line this time. We're not going to test for pluses or minuses. What we're going to do instead is we are going to plug each critical number and each one of the endpoints back into the original function, f of x. And it's a very simple concept. Basically, however many you have to plug in, whatever you get for your biggest answer out of all of them is your maximum, and whatever you get for the smallest is your minimum. So let's go ahead and try one out. So here's our function. We have f of x equals x cubed minus 3x squared plus 1. And I said over the given interval, and I give you a closed interval from 1/2 to 4. I asked you to find both the minimum and maximum, the absolute minimum and maximum. So let's start with the critical values. Start with f prime. The derivative work for this one's pretty straightforward. It's just power rule. So I multiply by 3 and lower that to x squared. On the second one, I multiply by 2. That would give me a 6 and lower that to x to the first. And the derivative of 1 is 0. It basically disappears. So there's my derivative. 3x squared minus 6x. It's never undefined. I don't have to worry about that. It's not a fraction. I don't have to worry about a denominator or anything like that. But I can set it equal to 0 and solve, basically. So 3x squared minus 6x equals 0. I would solve this one by factoring out common terms. You can factor out 3x, and that would leave you with x minus 2. So my two critical numbers here, I get x equals 0 from the x that I factored out, and I get x equals positive 2 from the x minus 2 that was left over. Now I look back at my interval. The 2 is fine, because 2 is between 1/2 and 4. 0 is not in my interval. So I'm just going to throw that one out. That one's gone. Remember, if you get a critical number that is not between these two numbers here, if it's not on that interval, don't use it. Throw it out. We're only worried about that little tiny segment of the graph. So once I've figured that out, I only have one critical number left. That means there's 3 things I need to check. I need to check x equals 2, I need to check x equals 1/2, and I need to check x equals 4. And all I'm doing, remember, you're not doing a number line this time. All you're doing is you're going back to your original function and plugging each one in. So let's do 2 first. That would be 2 cubed minus 3 times 2 squared plus 1, which would be, let's see, we would have 8. Minus 12, negative 4, plus 1 would be negative 3. Now, I don't know anything right now, because you won't know which one is the minimum or the maximum until you know all of them. So right now I have a negative number. That might be the minimum, it might be the maximum, I don't know. But we have to keep going. Let's do f of 1/2 next. That would be 1/2 cubed minus 3 times 1/2 squared plus 1. Let's see here. I'll do a little work on this one. That would be 1/8 minus, that would be a 3/4 plus 1. With a common denominator, that would be 1/8 minus 6/8 plus 8/8, which would end up giving us negative 5. That would end up giving us 3/8. Positive 3/8. Let's see if we can squeeze our last one. I don't have a ton of space left, but the last one I need to do is find f of 4. And that would be 4 cubed minus 3 times 4 squared plus 1, which would be 64 minus 48 is 16 plus 1 is 17. So now that I've gotten these 3 answers, these are the 3 numbers I'm comparing. I have a negative 3, I have a 3/8, and a positive 17. So I can tell now the negative 3 is the smallest of those 3 numbers. So that's my minimum. The smallest value that function reaches on that interval is negative 3. And you also know that it happens at x equals 2. The biggest number is the 17. So the 17 is the maximum. And the maximum happens at x equals 4. Now the 1/2 is just nothing. I mean, it's part of the graph, but it's not the minimum or the maximum because 3/8 is not the biggest or the smallest number. So you can see what we did there. We found critical values. We tested each critical value plus the endpoints of the interval by just plugging them into the original function, and all we're doing is looking for the biggest or smallest one. All right, the last thing I want to do, I went to Desmos and I graphed this function, just to give you guys one more visual of what's actually happening here. So this is the function. This is what it looks like. Now, if you notice, if you look at it, yeah, the way it's written, without doing a closed interval, this doesn't have a minimum or a maximum. this graph right here would keep going forever this way. So that would not have a minimum. And then up here, same thing. It would keep going forever up this way, so it wouldn't have a maximum. But we did chop it off. We said we're going to start at 1/2, which would be right here, and we're going to end at 4, which would be right here. So basically, I am starting my graph at this point. I'm getting rid of all of this. And the only part of the graph I'm actually using starts here, dips down, goes up, and it's going to end at 4, which is right here. Make it kind of stand out there. So this part of the graph, this light blue part, is the only part that we're using. The purple, we got rid of all of it. Now, if you just focus on that light blue part, what you can see is that right here is the maximum. And it matches our answer. The maximum happened when x equals 4, and it equaled 17. That's the highest it reached. And the minimum would be right here at the bottom. It happened at x equals 2, and it equaled -3. I mean, it matches our work perfectly. Now over here, this was the last point that we tested. We plugged in 1/2 and we got whatever the fraction was, 5/8, I think, or 3/8. But you can see it's not the minimum or maximum. It was one of the endpoints, but it is not the highest or lowest point. But those 3 points that we tested were the only ones that could have possibly been the minimum or the maximum. And we just figured it out by plugging them in.